In this video, I'll talk about how to calculate the area between curves. The video will also include a few examples where we should calculate the area which is bounded by different curves. If we have a specific area which is bounded by the two graphs for the function fx, that could be like this one here, and the function gx, which is this one here, then we can see that these two curves for the two functions d of x and f of x create an area, which is the one I will label A. And if we would like to find the area of this A here, we can use integration as we have learned. So how will we actually do that? Well, first of all, we'll look into the limits of this area here. We see that we have an intersection point between the two graphs for g of x and f of x in x equals a and x equals b. We could label these two intersection points here. If we then consider, when we talked about the definite integral, and we start by considering just the curve for the function fx, then let's sketch it down here. That must approximately be the one here. That is just the curve for fx taken from up here. Then we can see that if we have the same limits here, a and b, then we remember from when we talked about the definite integral that we could calculate this area here below the graph or the curve for fx. We could label that a1, this area here, to be equal to a1 must be given by the definite integral from a to b of fx dx. That was what we considered when we talked about the definite integral. And with the same very argument, we can look at the definite integral for the function gx, which is this one here. I have tried to sketch the same function as we have up here. Then we see that if we look into the same limits as we did up here, a and b, then this small area down here, which we can label a2, we can calculate as the definite integral with the limits a and b of gx dx. So then we can see that if we take the so-called upper function, which in this case must be fx, and subtract the area of the lower function, which in this case must be gx, then we will exactly have the area which is equal to the area in between the functions dx and fx. Alright, so let's sketch that here. That a, which is the area, from up here, must be equal to a1 minus a2. And since a1 is given by the definite integral from a to b of fx dx, and a2 is given by the definite integral from a to b of gx dx, then we can equal that into that the area of the region which is bounded by the two curves for fx and dx must be equal to the definite integral from a to b, the two intersection points a and b between the two graphs, of fx minus gx dx. So as simple as that. If we would like to find the area bounded by the two curves fx and gx in this example here, we take the definite integral of the upper function and subtract that with the lower function. Let us look at one example where we use this. So in this example here, we should find the area enclosed by the two graphs fx equals minus x squared plus 4x and dx equals minus x plus 4. So what we just looked at before was that we could find the area as the definite integral between the upper function and the lower function. So the first thing we need to realize here is which one of these, fx and gx, is the upper function and which one is the lower function. What we could start with could be to illustrate the curves for these two functions here. So let's do that. Well, we see that here we have a parabola, which will look something like this. It must have an intersection point of 4 over here. That must be the fx, which we have here. And gx is a linear function intersecting the y-axis in 4 and have a negative slope of 1. So that must be something like this. That must be gx. So here we can see that the area which is enclosed or bounded by fx and gx must be this one here. So that is the one which I'm looking for, A. So now it's quite obvious for us that the upper function must be fx and the lower function must be gx in this case here. So what we need to do before we are able to find the area will be to find the intersection points between the two graphs, because that's where we have the limits to our integral. So intersection point between fx and gx. That's the first thing which we will calculate. So when fx and gx intersect, the two, they have a point in common, as you know, so that it will be when fx is equal to gx. In other words, when minus x squared plus 4x equals minus x plus 4. So that will be altogether minus x squared plus 5x minus 4 equals 0. And when you solve this second degree polynomial, you will get that x is either equal to 4 or x is equal to 1. So that is our two intersection points. So this must be 1, which we have here. So now we have the limits to our integral. And now we are ready to calculate the area, which we have labeled A. So A must be equal to the definite integral from the lower limit 1 to the upper limit 4 of the upper function, which in this case is fx, subtracted with the lower function, which in this case is dx. So since fx is defined as minus x squared plus 4x, and we subtract that with gx, which is defined as minus x plus 4 dx, then we can simplify this a bit before we find the integral. So we have 4 and 1, so that must be minus x squared, and then we have plus 4x plus 1x, that will give me plus 5x minus 4 dx. Yes, and the integral of that must then be minus 1/3 x to the power of 3 plus 5 over 2 x squared minus 4x, and the limits which we have here will still be 4 and 1. So we insert our values for the limits, the upper limit, as we normally do for definite integrals, minus 1/3 times 4 to the power of 3 plus, like that, minus 4 times 4 subtracted with the lower limit, like that. And when you simplify that, that altogether gives you 9 over 2 or 4.5, whatever you prefer. So the area, we have now calculated the value of the area A to be equal to 9 over 2. So far we haven't considered whether one of the functions are negative or not, but it's not a problem. because the area which is bounded by the two functions will still be, we will still be able to calculate that by the definite integral between the upper function and the lower function, as we have seen so far. Why that is the case is what we'll look at now. Let's consider that we have a function f(x) and a function g(x), and we should calculate the area which is bounded by these two graphs. So that will be this area. I can label that A here. Then we do it in the exact same way as we just saw for the previous example, because if we make a parallel displacement of this area here up here, that means that we add, you could say, a constant c to the function f(x). It will be up here. That will be f(x) plus c, and we add the same constant to the function g(x). That could be, then it will look something like this. That will be g(x) plus c. Then we will have the same area up here, and it will be in the positive region. As you can see, the area is the very same thing as the one which we have made down here. So if we should find the area of what we have up here, we could call that A equals then the definite integral, and let's say that the limits, we label those A and B. They will be the same, of course. We've just make a parallel displacement of the area in question, so it will be the definite integral from A to B of, and up here, the upper function, f(x) plus c dx, subtracted with the definite integral of the lower function, which is gx plus c dx. As we have learned, we can split up the two integrals, so it will look like the definite integral from a to b of f(x) dx plus c dx, subtracted with, and then we split up also this integral from a to b of gx dx and c dx. So we see that when we expand this bracket here, we have all left the definite integral from f(x) dx plus the definite integral of c dx minus the definite integral for c dx, and that one is limited. And then we have left the definite integral from a to b of gx dx. So that will altogether give me that the area of the region is equal to the definite integral from a to b of f(x) minus gx dx. So now we've seen that it doesn't matter whether we have a positive or a negative function to look at. The area which is bounded between curves can be calculated as a definite integral between the upper function and the lower function, no matter where we have this area placed. As the final thing in this video, I have chosen to include a bit more complex example as the first one which we have seen. In this example here, we should find the area which is enclosed by, first of all, gx equals half x minus 3/2, and the function f(x), which is a partly defined function. The function is defined by x squared minus 10x plus 33 when x is smaller than or equal to 7. And the function f(x) is defined as minus 2x plus 26 for all values of x greater than 7. We have one more limit to our area, and that is x equals 4. Down here I've tried to illustrate this area we should calculate. First of all, we have x equals 4, that is the graph which we have here. The function gx is the linear function which I've sketched here, half x minus 3/2, and then I have inserted the function f(x), which is defined as this parabola here. For x being smaller than 7, that must be here, and for x greater than 7, f(x) is defined as minus 2x plus 26, which is the linear function you can find here. So the area which we are looking for, must obviously be this one here. So in order for us to figure out what the area is actually equal to, one thing we need to start with will be to find the limits. We have a limit here of 4 given in the assignment. We have a split here at 7. And then we have an intersection point here which we should calculate. So that we'll start with. Obviously at this point here the intersection point will be between fx defined as minus 2x plus 26 and dx. So the intersection point will be the first thing which we will calculate. So that will be minus 2x plus 26 equals half x minus 3 over 2. And when you solve that one here, you will find that when x is equal to 11, the two functions will intersect. So now we're actually there, because now we can calculate the area A. We need to split it into different intervals, because we can see that from 4, x equals 4, up to x equals 7, the area is given by the definite integral of the upper function fx minus the lower function gx. So that must be from 4 to a 7 fx, and in that interval fx is defined as x squared minus 10x plus 33 subtracted with the lower function gx, which is defined as half x minus 3 over 2 dx. So that was the first area here, which we have calculated here. Then we have to add that with the small triangle here, the second part of our area. So that must be from 7 to 11. The upper function here is still fx, but fx defined as minus 2x plus 26, subtracted with the lower function gx, which is half x minus 3 over 2 still dx. So now we just need to simplify this, insert our values for the limits. That I will leave you to do on your own, and then you will find out that the area is altogether given by 43.25. So that's how you do it. If you should find the area enclosed by curves, then you simply need to look into which one of these curves will be the upper function and which one will be the lower function, and then you will find the area to be equal to the definite integral of the upper function minus the lower function with the limits as the intersection points given. Thank you for listening.